How's it going, Dr. O?
Good. How are you, Jalen?
Pretty good. My camera will come on whenever I'm finished eating.
Take your time. It's one of the benefits of studying remotely. Okay. Let's see. Okay, we're just about here. Okay, so last topic in the course, we talked about things like linear independence and spanning and vector spaces and eigenvalues, eigenvectors. The last major topic in the course has to do with what is called dot product and inner product.
Oh, Dr. O, you told me to remind you to talk to us about our test.
Oh, yes, right. Thank you. So those of you keeping an eye on the calendar, note that we have one more midterm coming up on Friday, and some of you have conflicts with other courses. So what I have decided to do, instead of posting it Friday and having it due on Monday, I'm going to post it on Friday, and we'll just say it's due on Wednesday, and you can use any hour period, any time between Friday and Wednesday to do it. So hopefully that will work with everybody's schedule. Okay? Cool. Okay. So if you note what we've done so far, in our vector spaces, so we've had lots of examples of vector spaces. We talked about, R2, R3, R basically anything, Rn. We also talked about a vector space, P2, all the polynomials of degree at most 2, etc. We've talked about vector addition and scalar multiplication. We've talked about linear independence and dependence. We talked about vectors which span. We talked about the zero vector. Lots of different concepts that have to do with vectors. But we haven't talked about length and angle. And in fact, a vector space doesn't have to have any notion of length or angle at all. If you take a look back at the definition of a vector space, it doesn't refer to anything that deals with length and angle. the vector space, as we've defined it, has no concept of length or angle. Which makes that definition that we got from our high school physics teachers about vectors, a quantity with magnitude and direction. Magnitude means length, and basically direction means kind of angles with other things. Makes that very problematic because vector spaces don't come with ideas of length or angle. However, we can take a vector space and add what's called a dot product or an inner product. So we can add the concept of a dot product or inner product. And that will make length or angle make sense. My point in saying this is that the idea of length and angle flowing from dot product and inner product, that's not part of the definition of a vector space. That's optional equipment. So let's see. If you buy a car, you can expect to get, an engine, and you can expect to get a chassis, and you can expect to get what's something else that's definitely going to come in a car.
Steering wheel.
A steering wheel almost certainly comes in a car. You can expect to get all these things. These are things that you expect to come in a car. They're part of the definition of a vector space. But power seats, if your car comes without power seats, it's still a car. So vector spaces don't come with dot product or inner product. That's optional equipment. And if you add them, then you can, so if you add a power seat, then you can do things like, press the button and slowly move towards a steering wheel. That's what a power seat does. But it's optional equipment. I was going to say like air conditioning, but most cars come with air conditioning nowadays.
Heated seats.
Heated seats. I am a big fan of heated seats. Which tells me that things have changed since my grad school days. When I bought my, third car, I guess. What I really wanted in a car were two things that I'd never had. One was cruise control, and I got that. And the other was a cup holder. So my standards were very basic at that point. I got the cup holder too. I was very happy about that. So let's see. So let's consider R2. And we'll let U be the vector U1 and U2. And we'll let V be the vector V1, V2. These will be two vectors in R2. They're in R2, obviously, because we have two components. 1, 2. It's not difficult to compute the dot product of these two vectors. U dot V, you take the first components and multiply them. You take the second components and multiply them, and you add them up. That's all there is to it. So if I take the vector 1, 2, and dot it with the vector 3, 4, 1 times 3 plus 2 times 4, 3 plus 8, 11. Not difficult. And as long as we're here, I might as well just show you how to compute dot product in any dimensional space. If we consider R3, if I have a vector U, this time it's going to have 3 components, U1, U2, U3, and V, V1, V2, V3. If you had to guess how to compute the dot product of these two vectors, I'm willing to believe you would guess correctly. U dot V is U1 V1 plus U2 V2 plus U3 V3, boom. Just put a little dot between them. So I don't know if what example's worth it, but we might as well. 1, 2, 3, dot with 4, 5, 6. 1 times 4 plus 2 times 5 plus 3 times 6. 4 plus 10 plus 18, 32. So we didn't mess that up. Let's go. And in R4, does anybody feel like they're not sure what to do in R4 or R5 or R6? I didn't think so. So let me give you a geometric interpretation of dot product. Doesn't matter what dimension you're in here. The dot product, U dot V, is equal to the length of U, which I'll denote like this. That's the length of the magnitude of U. Times the length of V times cosine of theta. And perhaps as a special case of that, let's look at what happens if we take the dot product of a vector with itself. Let's say I have U as the vector U1, U2. So we're in R2. So saying that its that u is u1, u2 means we come out u1 on this axis and u2 on this axis. So if this is the x1 axis and this is the x2 axis, that's where we go. That's where that vector is. So u dot u is going to be u1, u2 dot u1, u2. So we end up with u1 times u1, u1 squared, plus u2 times u2, u2 squared. But the length of u just with the Pythagorean theorem I just learned something interesting about Pythagoras recently, that some historians think that he may not have existed at all. That, yeah, I know, that they think that the Pythagoreans, the group of people called the Pythagoreans, they definitely existed. But some people think that they just sort of invented this guy as like the founder of their movement. He never really existed.
Pythagoras, the Santa Claus of math.
What's that?
The Santa Claus of math.
Yeah, that Pythagoras never wrote anything down. We have no direct historical evidence of Pythagoras. The only history we have of Pythagoras was written after Pythagoras was supposedly dead. So we don't know for sure whether this guy existed or not. I didn't know that. And I feel like I should have, but I didn't. So let's see. By the Pythagorean theorem, the length of this line, the length of this vector is just the square root of this squared plus this squared. So the length of u is equal to the square root of u1 squared plus u2 squared. So in other words, it's equal to the square root of u dotted with itself. So if I take a vector and dot it with itself, just by squaring both sides here, I get the magnitude of u all squared. When you take a vector and dot it with itself, you get its length squared, because its length is just the square root of it dotted with itself. This equals this is exactly the same as saying that equals that. So let's just practice with that and this. I think I want to leave both of those on the blackboard, which means we have to erase this. So find the angle between u equals the vector 1, 2. Now let's do it in R3. And v equals the vector 4, 5, 6. So we want this theta. First thing we're going to need is the length of u and the length of v. That's not hard. So the length of u is going to be the square root of u dotted with itself. The square root of, if I take this and dot it with itself, I have 1 times 1 plus 2 times 2 plus 3 times 3. In other words, 1 squared plus 2 squared plus 3 squared. So let's see, 9 plus 4 is 13, 14, so this is the square root of 14. And length of v is going to be the square root of v cross v dot v. So that's just going to be square root of 4 squared plus 5 squared plus 6 squared, square root of, let's see, 36 plus 25, 46, 56, 61, 71, 77, I guess. You have to tell me if I made a mistake. Yeah, that looks right. So the length of u is, excuse me, square root of 14. The length of v, the magnitude of v is square root of 77. And let's compute the dot product of the two of them. U dot v equals 1 times 4 plus 2 times 5 plus 3 times 6 4 plus 10 plus 18, that's 32. I think we already did that. So we have u dot v equals the length of u times the length of v times cosine of the angle that we care about. That's what we want, the angle between these two vectors. Let's just put all these numbers we've already computed. U dot v is 32. The length of u is root 14. The length of v is root 77. And cosine of theta, that's what we want. We get cosine of theta by itself. 32 over root 14 times root 77. And so theta is going to be the arc cos. So if you prefer to write that as cos the minus 1, that's fine. Just remember that the minus 1 doesn't mean 1 over, it means the inverse of 32 over root 14 root 77.
Oh, you didn't have to move. I thought you froze for a sec.
Oh, no. I mean, no more than usual. I don't mean, I know it's been a while since you've taken trigonometry, but I assume trigonometry is pretty comfortable for you. Is everybody still okay with the inverse trigonometric functions, inverse sine, inverse cos, inverse tan? Is that still something that makes sense? That sine takes an angle and gives you a ratio of 2 sides, but inverse sine, like arc sine, takes the ratio of 2 sides and gives you back an angle. And that those buttons are on your calculator. Everybody still good with that? Cool. Okay. Okay. So if I give you two vectors in R2, R3, R4, R5, you should be able to compute the length of each of those vectors. You should be able to compute the angle between those vectors, and so on. Two vectors are said to be orthogonal if
They're said to be what?
orthogonal. Even though I'm defining it, I forgot that was a new word. So two vectors are said to be orthogonal, orthogonal. If their dot product is 0. So for example, about just a sec. That'll do it. If I take u dot v, I get 2 times 3 plus 4 times 1 plus negative 2 times 5. So that's 6 plus 4 is 10 minus 10 is 0. So geometrically speaking, what does it mean for two vectors, let me say two non-zero vectors, to be orthogonal? Geometrically speaking, what does it mean for two non-zero vectors to be orthogonal?
I believe that means they're at a right angle, correct?
Yeah, that's exactly what it means. So if I take u dot v, if this is going to be 0, the dot product is 0, and this is equal to the length of u times the length of v times cosine of theta. If u and v, well, let me wait till you write that down. So if u and v have dot product 0, and u dot v is the length of u times the length of v times cos theta, that means the length of u times the length of v times cos theta is 0. But if these are not zero vectors, then the length of u isn't 0, and the length of v isn't 0. But so the only way that this product could be 0, length of u times length of v times cosine theta, is if cosine theta equals 0. So theta is 90 degrees. Or pi over 2 if you like radians. So the angle, so the two vectors are perpendicular. So orthogonality basically means perpendicular. So two non-zero vectors are orthogonal. The angle between them is a right angle, just like you said. They're perpendicular. And all the stuff we're talking about today depends on having a dot product, depends on having an inner product. An inner product is just a dot product is just an example of an inner product. And I haven't explicitly explained what an inner product is yet, but maybe we'll circle back around to that. Maybe we won't. So the idea of parallel exists in a vector space without a dot product or an inner product, but the idea of perpendicular doesn't. That only makes sense if we have a dot product or an inner product. Okay, so let's see. And note, if I take the zero vector and dot it with anything, since it's just the length of this times the length of that times cosine of theta, the length of that's already zero, this just equals zero. So the zero vector is orthogonal to every vector. Zero vector is orthogonal to everything.
I'm like really impressed that you covered like the first half of Calc 3 in like 32 minutes.
It's not the first half of Calc 3. You're exaggerating. There's a lot more to the first half of Calc 3 than that. But yes, at some schools, you have to take linear algebra before you take Calculus 3. And at other schools, they take linear algebra and they stick it together with differential equations, and they make a course called Linear Algebra and Differential Equations, which I really hate because you can't do either subject justice if you're smushing them into one course. But yeah, the idea behind multivariable calculus makes a lot more sense once you have a little bit of linear algebra under your belt. Are any of you taking Calculus 3 next semester?
I took it last semester.
You took it last semester, yeah. But last semester, I don't think I taught it. I'm pretty sure I didn't.
No, Dr.
Yeah.
I think
I'm
I'm
not
taking
sure
it next
when.
semester.
What's that?
I said I think I'm taking it next semester.
Oh, cool. Yeah, I think several of you are. Kayla put up her hand, and Nick says he's taking it, and you're taking it. So yeah, so several of us will all be back together for Calculus 3. It's a fun calculus class. Multivariable calculus. It might be clear to you, or might not be clear to you yet, what linear algebra has to do with that. But it definitely has something to do with it. I don't know if I've mentioned this to you, but my wife, Dr. Warren, and I have this disagreement as to what's the best calculus. And she absolutely thinks that the best calculus is Calculus 3. She loved that the very best. And I don't know if I can pick a favorite. I sort of love them all. So, okay, let's see. We've talked about orthogonality. We've talked about finding the angle between two vectors. I want to talk a little bit about the properties of dot product. So I'm not going to make a big deal about this. I think most of these are going to feel pretty natural. U dot V and V dot U are the same. That should be obvious. Since you build dot product out of times and plus, and the order in which you multiply things doesn't matter, it doesn't matter which order you take dot product in. U dot V plus W equals U dot V plus U dot W. In other words, dot product distributes over vector addition.
Wait, what does that say? Yeah, no, the P word.
Properties.
Oh, properties.
Properties of dot product. Oh yeah, a little hard to read on the screen. Sorry about that. I'm gonna wait till you catch up. Okay, so if I take a constant times U and dot that with V, that's the same as taking the dot of U and V first and then multiplying by C. Or I could put the constant in front of V. Really, it doesn't matter where it goes. So in other words, dot product commutes with vector multiplication, with scalar multiplication, I should say. And last, if I take the dot product of a vector with itself, that's always at least as big as 0. That shouldn't come as a surprise. If you're just taking the first component and squaring it, the second component squaring it, if there's a third component squaring that and adding them all up, it's going to come out positive. And the dot product of a vector with itself equals 0. The only way that can happen is if the vector itself is the 0 vector. The only vector which has a 0 dot product with itself is the 0 vector. I want to talk a little bit about orthogonal complements. We know orthogonal means perpendicular. That's compli with an E, not compli with an I.
You should look at what we said in the chat.
Oh, I will.
It's very on topic of what we were talking about while you were talking.
Oh, so is the math is fake? Does that have to do with Pythagoras?
Yeah.
Well, you know, there's a whole subject about the philosophy of mathematics, and there's even a subject called the sociology of mathematics. Um, but when you talk about like the STEM subjects, like math has its own letter, M, right? Math is not a science, in the sense that physics or chemistry or biology is a science. Um, a science this attempts to describe some aspects of the actual real world. And math is not constrained that way. Math is it's a philosophy. It's a way of reasoning. And so you're right in the sense when you say it's fake. What you mean, I think, is that it's not connected necessarily to reality. But that can be very freeing. You can do things in mathematics that you can't do in the sciences. And also, unlike something like physics, mathematics is sort of the only area where you can, that's in STEM, where you can actually have absolute truth. In the sciences, you can prove, you know that if you've taken a science course, you can prove that things are false. You can always falsify a scientific statement by finding a counterexample. But you can never prove that something is always true because somewhere out in the universe there may be something that states that this isn't true. For many years we thought that not Euclidean, we thought that Newtonian mechanics was right, and then Einstein said, well, not quite. And as a matter of fact, at that point we sort of rewrote our idea of what a scientific law should do. But in math, you can come up with something which is absolutely true. But the truth in mathematics is always of the form, if this, then that. So if we assume this, then that must be true also. Nobody's saying that the this is true. We're just saying that if it is, then that thing over there is also true. And so that's, you can have absolute truth in mathematics, but what you lose is the fact that it's not necessarily connected with anything. But if you take a look at Euclid's proof that there are infinitely many prime numbers, that is an absolutely true thing that will never be found false. But prime numbers are not necessarily anything that's connected, that's part of the real world. They're an abstract concept. Everything in math is an abstract concept, even things that you may not think of as abstract concepts. The number 3 is an abstract concept. You can't show me 3. You can show me 3 pencils. You could show me 3 books. You could show me 3 fingers. But 3 is the abstract idea which connects all those things. It's not something physical. And that's why it bothers me when people call the number I an imaginary number. Yes, it's imaginary, but so is 3. They're both imaginary. Calling I an imaginary number is nothing more than the rankest kind of numerical prejudice. They're all abstract concepts. I think I got a little taken off course there, but anyway, it's all interesting stuff. And yes, that was interesting to read. Calc 3 was easier than Calc 2. I'm glad to hear that. Although Calc 2 is Calc 2. Okay, right. Didn't see that before. So I think that my wife would agree with you that Calc 2 is her least favorite course. But I think that there is stuff in Calculus 2 which definitely doesn't suck. Which takes me to something else that's, again, off topic. But my youngest daughter and my wife have started this whiteboard in our house that they update periodically called Things About 2020 That Don't Suck. And they have a whole bunch of things over there, and I think it keeps them sort of upbeat. Okay, orthogonal complements. Consider a vector space V, whatever it is, and let W be a subspace of V. Remember what a subspace is. It's a smaller, could be the whole thing, but a vector space living inside another vector space. Then W, we use this symbol right here as like as a superscript. This is all the vectors that are in V such that V dot W equals 0, equals 0 for all W in W. In other words, in English, W, oh, and you read this W perp. Perp for perpendicular. So in other words, W perp is the set of all vectors which are perpendicular to everything in W. All vectors in V orthogonal. And remember, when you read orthogonal, you can think perpendicular to all vectors in W. All vectors which are orthogonal to all vectors in W. Let me see if I can give you a picture. Let's say V equals R3. And let's say W is some plane, some 2D subspace of R3. In other words, a plane through the origin. Goes on in all directions infinitely. So that plane goes through the origin because it's a subspace. Which vectors are perpendicular to every vector in that plane? So I have this plane going through space. Which vectors are perpendicular to every vector in that plane?
Wouldn't it be all of them?
No, definitely not. Because if I take a vector in the plane It's definitely not perpendicular to itself.
Oh, okay.
Which vectors are perpendicular to every single vector in that plane? So none of the vectors in the plane will qualify. They have to be vectors outside the plane. Which ones?
Are they the ones that have a dot product of 0? But I don't know. Which
Yeah, but where are they?
The origin.
The origin is definitely one of them. So the origin is definitely, like the 0 vector is definitely perpendicular to everything else, to everything in that plane. But are there others? Here's a hint. Yes. Where are they? Okay, I see I'm out of time. I'm going to let you think this one over. And we'll begin next class with this same question, and hopefully by then you'll have an answer for me. So just think it over. Don't forget, for those of you that are in my next class, I will be here to answer any questions that you might have of you as you work on your projects. But you can come or not come as you wish. There will be no lecture today. And for those of you that are not in my next class, I will see you all on Friday. And for those of you that are, I may see you in a few minutes, or I may see you on Friday. Take care.
Thank
Have
you.
a good day.
Thank you.